Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Data Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are deploying a batch pipeline in Dataflow. This pipeline reads data from cloud storage, transforms the data, and then writes the data into BigQuery. The security team has enabled an organizational constraint in Google Cloud, requiring all compute engine instances to use only internal IP addresses and no external IP addresses. What should you do? The options are: Option A, ensure that your workers have network tags to access cloud storage in BigQuery. Use Dataflow with only internal IP addresses. Option B, ensure that the firewall rules allow access to cloud storage in BigQuery. Use Dataflow with only internal IPs. Option C, create a VPC service controls perimeter that contains the VPC network and add Dataflow, cloud storage, and BigQuery as allowed services in the perimeter. Use Dataflow with only internal IP addresses. Option D, ensure that private Google access is enabled in the subnetwork. Use Dataflow with only internal IP addresses.
To arrive at the correct answer, we focus on the keywords: Dataflow, cloud storage, BigQuery, use only internal IP addresses and no external IP addresses.
The correct answer is option D, ensure that private Google access is enabled in the subnetwork. Use Dataflow with only internal IP addresses.
Why is this correct? D. Private Google access enables VM instances with only internal IP addresses to reach the external IP addresses of Google APIs and services, such as cloud storage and BigQuery. Why are the others incorrect? A. Network tags alone do not enable access to Google services from instances with only internal IP addresses. B. Firewall rules are necessary but insufficient. Without private Google access, instances without external IPs cannot route traffic to Google APIs. C. VPC service controls perimeters secure resources against data exfiltration but do not provide the necessary routing for internal IPs to access Google APIs.
You are running a Dataflow streaming pipeline, with streaming engine and horizontal autoscaling enabled. You have set the maximum number of workers to 1,000. The input of your pipeline is pub/sub messages with notifications from cloud storage. One of the pipeline transforms reads CSV files and emits an element for every CSV line. The job performance is low, the pipeline is using only 10 workers, and you notice that the autoscaler is not spinning up additional workers. What should you do to improve performance? The options are: Option A, enable vertical autoscaling to let the pipeline use larger workers. Option B, change the pipeline code and introduce a reshuffle step to prevent fusion. Option C, update the job to increase the maximum number of workers. Option D, use Dataflow Prime and enable right fitting to increase the worker resources.
To arrive at the correct answer, we focus on the keywords: Dataflow streaming pipeline, horizontal autoscaling enabled, maximum number of workers to 1,000, reads CSV files and emits an element for every CSV line, autoscaler is not spinning up additional workers.
The correct answer is option B, change the pipeline code and introduce a reshuffle step to prevent fusion.
Why is this correct? B. Dataflow fuses operations, limiting parallelization for high-fan-out transforms like reading lines from a single CSV. Introducing a reshuffle step breaks this fusion, allowing horizontal autoscaling to properly distribute the downstream work across more workers. Why are the others incorrect? A. Vertical autoscaling increases individual worker size, CPU/memory, which does not solve the lack of horizontal parallelization caused by step fusion preventing the pipeline from scaling out. C. The maximum number of workers is already 1,000 while only 10 are being used. Increasing the maximum limit will not fix the fusion issue preventing parallelization. D. Right fitting in Dataflow Prime optimizes resources for individual steps but does not break step fusion, which is the root cause preventing the pipeline from distributing work horizontally.
You have an Oracle database deployed in a VM as part of a virtual private cloud (VPC) network. You want to replicate and continuously synchronize 50 tables to BigQuery. You want to minimize the need to manage infrastructure. What should you do? The options are: Option A, deploy Apache Kafka in the same VPC network, use Kafka Connect Oracle Change Data Capture (CDC) and Dataflow to stream the Kafka topic to BigQuery. Option B, create a pub/sub subscription to write to BigQuery directly. Deploy the Debezium Oracle connector to capture changes in the Oracle database and sync to the pub/sub topic. Option C, deploy Apache Kafka in the same VPC network, use Kafka Connect Oracle Change Data Capture (CDC) and the Kafka Connect Google BigQuery Sync connector. Option D, create a data stream service from Oracle to BigQuery, use a private connectivity configuration to the same VPC network, and a connection profile to BigQuery.
To arrive at the correct answer, we focus on the keywords: Oracle database, replicate and continuously synchronize, BigQuery, minimize the need to manage infrastructure.
The correct answer is option D, create a data stream service from Oracle to BigQuery, use a private connectivity configuration to the same VPC network, and a connection profile to BigQuery.
Why is this correct? D. DataStream is a serverless CDC and replication service that continuously synchronizes data from Oracle to BigQuery. Using private connectivity allows secure access to the VPC, fully meeting the requirement to minimize infrastructure management. Why are the others incorrect? A. Deploying Apache Kafka and Kafka Connect requires significant effort to provision and manage the underlying infrastructure, which directly contradicts the requirement to minimize infrastructure management. B. Deploying Debezium connectors requires managing the compute infrastructure they run on, which violates the primary goal of minimizing the need to manage infrastructure. C. Deploying and maintaining Apache Kafka along with Kafka Connect requires substantial infrastructure management overhead, directly opposing the requirement to minimize infrastructure management.
You are deploying an Apache Airflow Directed Acyclic Graph (DAG) in a Cloud Composer 2 instance. You have incoming files in a cloud storage bucket that the DAG processes, one file at a time. The Cloud Composer instance is deployed in a subnetwork with no internet access. Instead of running the DAG based on a schedule, you want to run the DAG in a reactive way every time a new file is received. What should you do? The options are: Option A, 1. Enable private Google access in the subnetwork, and set up cloud storage notifications to a pub/sub topic. Point 2. Create a push subscription that points to the web server URL. Option B, 1. Enable the Cloud Composer API, and set up cloud storage notifications to trigger a cloud function. Point 2. Write a cloud function instance to call the DAG by using the Cloud Composer API and the web server URL. Point 3. Use VPC serverless access to reach the web server URL. Option C, 1. Enable the Airflow REST API, and set up cloud storage notifications to trigger a cloud function instance. Point 2. Create a private service connect, PSC, endpoint. Point 3. Write a cloud function that connects to the Cloud Composer cluster through the PSC endpoint. Option D, 1. Enable the Airflow REST API, and set up cloud storage notifications to trigger a cloud function instance. Point 2. Write a cloud function instance to call the DAG by using the Airflow REST API and the web server URL. Point 3. Use VPC serverless access to reach the web server URL.
To arrive at the correct answer, we focus on the keywords: Cloud Composer 2 instance, cloud storage bucket, subnetwork with no internet access, run the DAG in a reactive way every time a new file is received.
The correct answer is option C, 1. Enable the Airflow REST API, and set up cloud storage notifications to trigger a Cloud Function instance. Point 2. Create a Private Service Connect (PSC) endpoint. Point 3. Write a Cloud Function that connects to the Cloud Composer cluster through the PSC endpoint.
Why is this correct? C. Cloud Composer 2 private environments use Private Service Connect (PSC) to expose the Airflow REST API securely. A Cloud Function triggered by cloud storage can connect through this PSC endpoint to invoke the DAG. Why are the others incorrect? A. You cannot use a pub/sub push subscription directly to the web server URL, as the environment is private and requires authenticated Airflow REST API calls via PSC. B. The Cloud Composer API is used to manage the environment infrastructure, e.g., creating or updating it, not for triggering DAG runs. You must use the Airflow REST API. D. VPC serverless access alone cannot be used to reach the Cloud Composer 2 web server in a private environment. A Private Service Connect (PSC) endpoint is required.
You are planning to use cloud storage as part of your data lake solution. The cloud storage bucket will contain objects ingested from external systems. Each object will be ingested once, and the access patterns of individual objects will be random. You want to minimize the cost of storing and retrieving these objects. You want to ensure that any cost optimization efforts are transparent to the users and applications. What should you do? The options are: Option A, create a cloud storage bucket with AutoClass enabled. Option B, create a cloud storage bucket with an object lifecycle management policy to transition objects from standard to cold line storage class if an object age reaches 30 days. Option C, create a cloud storage bucket with an object lifecycle management policy to transition objects from standard to cold line storage class if an object is not live. Option D, create 2 cloud storage buckets. Use the standard storage class for the first bucket, and use the cold line storage class for the second bucket. Migrate objects from the first bucket to the second bucket after 30 days.
To arrive at the correct answer, we focus on the keywords. Access patterns of individual objects will be random, minimize the cost of storing and retrieving, transparent to the users and applications.
The correct answer is Option A, create a cloud storage bucket with AutoClass enabled.
Why is this correct? A. AutoClass automatically transitions objects between storage classes based on access patterns, optimizing storage and retrieval costs without requiring application changes or manual lifecycle rules, ensuring complete transparency. Why are the others incorrect? B. Object lifecycle management based purely on age, 30 days, is inefficient for random access patterns, as objects might be retrieved after 30 days, incurring higher cold line retrieval costs. C. Moving non-live, non-current object versions to cold line does not optimize the costs of storing and retrieving the active objects, which are randomly accessed. D. Using 2 separate buckets requires the application to know which bucket to query based on object age, which violates the requirement for cost optimization efforts to be transparent.
You have several different file type data sources, such as Apache Parquet and CSV. You want to store the data in cloud storage. You need to set up an object sync for your data that allows you to use your own encryption keys. You want to use a GUI-based solution. What should you do? The options are: Option A, use Storage Transfer Service to move files into cloud storage. Option B, use Cloud Data Fusion to move files into cloud storage. Option C, use Dataflow to move files into cloud storage. Option D, use BigQuery Data Transfer Service to move files into BigQuery.
To arrive at the correct answer, we focus on the keywords. Several different file type data sources, such as Apache Parquet and CSV, store the data in cloud storage, object sync, use your own encryption keys, GUI-based solution.
The correct answer is Option B, use Cloud Data Fusion to move files into cloud storage.
Why is this correct? B. Cloud Data Fusion is a fully managed, GUI-based data integration service that supports diverse formats like Parquet and CSV, provides cloud storage object syncs, and supports customer-managed encryption keys, CMEK. Why are the others incorrect? A. Storage transfer service is designed for bulk data movement from external locations to cloud storage, rather than acting as a GUI-based data integration pipeline with configurable object syncs. C. Dataflow is a code-based data processing service that requires writing Apache Beam pipelines, which violates the requirement for a GUI-based solution. D. BigQuery data transfer service is specifically used to automate data movement into BigQuery, whereas the requirement is to store data in cloud storage.
Your business users need a way to clean and prepare data before using the data for analysis. Your business users are less technically savvy and prefer to work with graphical user interfaces to define their transformations. After the data has been transformed, the business users want to perform their analysis directly in a spreadsheet. You need to recommend a solution that they can use. What should you do? The options are: Option A, use data prep to clean the data and write the results to BigQuery. Analyze the data by using connected sheets. Option B, use data prep to clean the data and write the results to BigQuery. Analyze the data by using Looker Studio. Option C, use Dataflow to clean the data and write the results to BigQuery. Analyze the data by using connected sheets. Option D, use Dataflow to clean the data and write the results to BigQuery. Analyze the data by using Looker Studio.
To arrive at the correct answer, we focus on the keywords: clean and prepare data, less technically savvy, graphical user interfaces, directly in a spreadsheet.
The correct answer is option A, use data prep to clean the data and write the results to BigQuery. Analyze the data by using connected sheets.
Why is this correct? A. Data prep provides a graphical user interface ideal for less technical users to clean and prepare data without writing code. Connected Sheets allows users to analyze BigQuery data directly in Google Sheets, satisfying the requirement for spreadsheet analysis. Why are the others incorrect? B. While data prep is the correct tool for data preparation via GUI, Looker Studio is a data visualization and dashboarding tool, not a spreadsheet application as requested by the users. C. Dataflow requires programming knowledge, Java, Python, or Go, to build data pipelines, making it unsuitable for less technically savvy users who prefer a graphical user interface. D. Dataflow requires programming skills, which the users lack. Looker Studio is a visualization tool, not a spreadsheet, failing to meet both of the primary user requirements.
You have two projects where you run BigQuery jobs. One project runs production jobs that have strict completion time SLAs. These are high-priority jobs that must have the required compute resources available when needed. These jobs generally never go below a 300 slot utilization, but occasionally spike up an additional 500 slots. The other project is for users to run ad hoc analytical queries. This project generally never uses more than 200 slots at a time. You want these ad hoc queries to be billed based on how much data users scan rather than by slot capacity. You need to ensure that both projects have the appropriate compute resources available. What should you do? The options are: Option A, create a single Enterprise Edition reservation for both projects. Set a baseline of 300 slots. Enable autoscaling up to 700 slots. Option B, create two reservations, one for each of the projects. For the SLA project, use an Enterprise Edition with a baseline of 300 slots and enable autoscaling up to 500 slots. For the ad hoc project, configure on-demand billing. Option C, create two Enterprise Edition reservations, one for each of the projects. For the SLA project, set a baseline of 300 slots and enable autoscaling up to 500 slots. For the ad hoc project, set a reservation baseline of 0 slots and set the Ignore Idle Slots flag to false. Option D, create two Enterprise Edition reservations, one for each of the projects. For the SLA project, set a baseline of 800 slots. For the ad hoc project, enable autoscaling up to 200 slots.
To arrive at the correct answer, we focus on the keywords: strict completion time SLAs, never go below a 300 slot utilization, spike up an additional 500 slots, ad hoc analytical queries, build based on how much data users scan rather than by slot capacity.
The correct answer is option B, create 2 reservations, one for each of the projects. For the SLA project, use an Enterprise Edition with a baseline of 300 slots and enable autoscaling up to 500 slots. For the ad hoc project, configure on-demand billing.
Why is this correct? B. This optimally provisions the SLA project with 300 baseline slots and 500 autoscaling slots for spikes. It also fulfills the requirement for the ad hoc project to be billed based on data scanned by using on-demand billing. Why are the others incorrect? A. A single reservation forces both projects into capacity-based billing, failing the requirement to bill the ad hoc project based on data scanned. C. Using an Enterprise Edition reservation for the ad hoc project incurs capacity-based billing instead of the required on-demand billing based on data scanned. D. A baseline of 800 slots is wasteful since only 300 are consistently needed. Furthermore, a reservation for the ad hoc project violates the requirement for on-demand billing.
You want to migrate your existing Teradata data warehouse to BigQuery. You want to move the historical data to BigQuery by using the most efficient method that requires the least amount of programming, but local storage space on your existing data warehouse is limited. What should you do? The options are: Option A, use BigQuery Data Transfer Service by using the Java Database Connectivity (JDBC) driver with fast export connection. Option B, create a Teradata Parallel Transporter (TPT) export script to export the historical data and import to BigQuery by using the BQ command line tool. Option C, use BigQuery Data Transfer Service with the Teradata Parallel Transporter (TPT) build utility. Option D, create a script to export the historical data and upload in batches to cloud storage. Set up a BigQuery Data Transfer Service instance from cloud storage to BigQuery.
To arrive at the correct answer, we focus on the keywords: Teradata data warehouse, least amount of programming, local storage space, is limited.
The correct answer is option A, use BigQuery Data Transfer Service by using the Java Database Connectivity (JDBC) driver with fast export connection.
Why is this correct? A. Using the BigQuery Data Transfer Service with a JDBC fast export connection minimizes custom programming and directly transfers data over the network, avoiding the need for large amounts of local storage. Why are the others incorrect? B. Creating custom TPT export scripts requires more programming effort and typically relies on local storage space for the exported data, violating both constraints. C. Using the TPT to build utility requires sufficient local storage space on the Teradata data warehouse to extract the data before uploading it, which is not suitable when storage is limited. D. Developing custom scripts to export and upload data requires significant programming effort. Additionally, batching data locally before uploading still consumes limited local storage space.
You are on the data governance team and are implementing security requirements. You need to encrypt all your data in BigQuery by using an encryption key managed by your team. You must implement a mechanism to generate and store encryption material only on your on-premises hardware security module, HSM. You want to rely on Google-managed solutions. What should you do? The options are: Option A, create the encryption key in the on-premises HSM and import it into a Cloud Key Management Service, Cloud KMS's key. Associate the created Cloud KMS key while creating the BigQuery resources. Option B, create the encryption key in the on-premises HSM and link it to a Cloud External Key Manager, Cloud EKM, key. Associate the created Cloud KMS key while creating the BigQuery resources. Option C, create the encryption key in the on-premises HSM and import it into Cloud Key Management Service, Cloud HSM, key. Associate the created Cloud HSM key while creating the BigQuery resources. Option D, create the encryption key in the on-premises HSM. Create BigQuery resources and encrypt data while ingesting them into BigQuery.
To arrive at the correct answer, we focus on the keywords: encrypt all your data in BigQuery, encryption key managed by your team, generate and store encryption material only on your on-premises hardware security module, HSM, rely on Google managed solutions.
The correct answer is option B. Create the encryption key in the on-premises HSM and link it to a cloud external key manager, Cloud EKM, key. Associate the created Cloud KMS key while creating the BigQuery resources.
Why is this correct? The Cloud EKM allows you to use keys managed in a supported external key management system, like an on-premises HSM. This ensures the encryption material remains only on your HSM while relying on managed solutions. Why are the others incorrect? A. Importing the key into Cloud KMS copies the encryption material to Google Cloud, violating the requirement to store it only on the on-premises HSM. C. Cloud HSM manages keys within Google Cloud's hardware, which violates the strict requirement to store encryption material only on your on-premises HSM. D. Manually encrypting data before ingestion, client-side encryption, does not fulfill the requirement to rely on Google-managed solutions like Cloud EKM seamlessly integrated with BigQuery.
You maintain ETL pipelines. You notice that a streaming pipeline running on Dataflow is taking a long time to process incoming data, which causes output delays. You also noticed that the pipeline graph was automatically optimized by Dataflow and merged into one step. You want to identify where the potential bottleneck is occurring. What should you do? The options are: Option A, insert a reshuffle operation after each processing step, and monitor the execution details in the Dataflow console. Option B, insert output sinks after each key processing step, and observe the writing throughput of each block. Option C, log debug information in each parto function, and analyze the logs at execution time. Option D, verify that the Dataflow service accounts have appropriate permissions to write the processed data to the output sinks.
To arrive at the correct answer, we focus on the keywords: streaming pipeline running on Dataflow, taking a long time to process, graph was automatically optimized by Dataflow and merged into one step, identify where the potential bottleneck is occurring.
The correct answer is option A. Insert a reshuffle operation after each processing step, and monitor the execution details in the Dataflow console.
Why is this correct? A. Inserting a reshuffle operation prevents Dataflow's fusion optimization, forcing the pipeline into separate steps. This allows you to monitor metrics for each step individually in the Dataflow console to accurately identify the bottleneck. Why are the others incorrect? B. Inserting output sinks introduces unnecessary I/O overhead and pipeline complexity. It is an inefficient and non-idiomatic way to isolate fused steps for performance debugging. C. Adding debug logging to every parto in a streaming pipeline can severely degrade performance and generate excessive logs without unfusing the steps for proper metric monitoring. D. The scenario describes a performance issue: processing takes a long time, not an access denied error. Permission checks will not help identify processing bottlenecks.
You are running your BigQuery project in the on-demand billing model and are executing a change data capture (CDC) process that ingests data. The CDC process loads 1 GB of data every 10 minutes into a temporary table, and then performs a merge into a 10 TB target table. This process is very scan-intensive, and you want to explore options to enable a predictable cost model. You need to create a BigQuery reservation based on utilization information gathered from BigQuery monitoring and apply the reservation to the CDC process. What should you do? The options are: Option A, create a BigQuery reservation for the dataset. Option B, create a BigQuery reservation for the job. Option C, create a BigQuery reservation for the service account running the job. Option D, create a BigQuery reservation for the project.
To arrive at the correct answer, we focus on the keywords: BigQuery project, predictable cost model, create a BigQuery reservation, apply the reservation.
The correct answer is option D, create a BigQuery reservation for the project.
Why is this correct? D. BigQuery capacity commitments, reservations, are assigned at the project, folder, or organization level. You cannot assign a reservation directly to a dataset, specific job, or service account. Assigning it to the project covers the CDC process running within it. Why are the others incorrect? A. BigQuery reservations cannot be assigned at the dataset level. They are assigned to a project, folder, or organization. B. BigQuery reservations cannot be assigned to individual jobs. They are applied to the project where the jobs run. C. BigQuery reservations cannot be assigned to a service account. They must be assigned to an entire project, folder, or organization.
You are designing a fault-tolerant architecture to store data in a regional BigQuery dataset. You need to ensure that your application is able to recover from a corruption event in your tables that occurred within the past 7 days. You want to adopt managed services with the lowest RPO and most cost-effective solution. What should you do? The options are: Option A, access historical data by using time travel in BigQuery. Option B, export the data from BigQuery into a new table that excludes the corrupted data. Option C, create a BigQuery table snapshot on a daily basis. Option D, migrate your data to multi-region BigQuery buckets.
To arrive at the correct answer, we focus on the keywords: recover from a corruption event, within the past 7 days, lowest RPO, most cost-effective solution.
The correct answer is option A, access historical data by using time travel in BigQuery.
Why is this correct? A. BigQuery time travel automatically retains historical data for 7 days, enabling seamless recovery from corruption with near zero RPO and no extra cost, making it the most cost-effective solution. Why are the others incorrect? B. Exporting data into a new table does not inherently recover data from before the corruption event and is more complex than using built-in time travel. C. Daily snapshots incur additional storage costs and have a higher RPO, up to 24 hours, compared to time travel, which automatically provides point-in-time recovery. D. Multi-region buckets provide geographic redundancy but do not protect against logical data corruption, as the corrupted data would simply be replicated.
You are building a streaming Dataflow pipeline that ingests noise-level data from hundreds of sensors placed near construction sites across a city. The sensors measure noise level every 10 seconds and send that data to the pipeline when levels reach above 70 dBA. You need to detect the average noise level from a sensor when data is received for a duration of more than 30 minutes, but the window ends when no data has been received for 15 minutes. What should you do? The options are: Option A, use session windows with a 15-minute gap duration. Option B, use session windows with a 30-minute gap duration. Option C, use hopping windows with a 15-minute window and a 30-minute period. Option D, use tumbling windows with a 15-minute window and a 15-minute with allowed lateness operator.
To arrive at the correct answer, we focus on the keywords: window ends when no data has been received for 15 minutes.
The correct answer is option A, use session windows with a 15-minute gap duration.
Why is this correct? A. Session windows group events occurring closely together. They dynamically close when a specified gap duration of inactivity occurs, which perfectly matches the requirement to end the window when no data is received for 15 minutes. Why are the others incorrect? B. A 30-minute gap duration would keep the session window open for 30 minutes of inactivity, failing to meet the requirement to close after 15 minutes of no data. C. Hopping windows are based on fixed time intervals and periods, not activity. They cannot dynamically close based on a 15-minute period of inactivity. D. Tumbling windows use fixed, non-overlapping time intervals. They do not close based on a lack of incoming data, and allowed lateness only handles delayed records.
You are creating a data model in BigQuery that will hold retail transaction data. Your two largest tables, sales_transaction_header and sales_transaction_line, have a tightly coupled immutable relationship. These tables are rarely modified after load and are frequently joined when queried. You need to model the sales_transaction_header and sales_transaction_line tables to improve the performance of data analytics queries. What should you do? The options are: Option A, create a sales_transaction table that holds the sales_transaction_header information as rows and the sales_transaction_line rows as nested and repeated fields. Option B, create a sales_transaction table that holds the sales_transaction_header and sales_transaction_line information as rows, duplicating the sales_transaction_header data for each line. Option C, create a sales_transaction table that stores the sales_transaction_header and sales_transaction_line data as a JSON data type. Option D, create separate sales_transaction_header and sales_transaction_line tables and, when querying, specify the sales_transaction_line first in the where clause.
To arrive at the correct answer, we focus on the keywords: BigQuery, two largest tables, tightly coupled immutable relationship, rarely modified after load, frequently joined when queried, improve the performance of data analytics queries.
The correct answer is option A. Create a sales_transaction table that holds the sales_transaction_header information as rows and the sales_transaction_line rows as nested and repeated fields.
Why is this correct? A. Denormalizing using nested and repeated fields is a BigQuery best practice for tightly coupled, one-to-many relationships that are frequently joined and rarely modified. It avoids expensive join operations and improves query performance. Why are the others incorrect? B. Duplicating header data flattens the table but significantly increases storage overhead and can make queries less efficient than using nested and repeated fields. C. Storing data as JSON adds processing overhead for parsing the JSON during queries, degrading performance compared to natively typed nested and repeated fields. D. Keeping tables separate and relying on query clauses does not resolve the performance issue of joining large tables, which is less optimal than denormalization.